Hello ladies and gentlemen, this is Dean from Multiply, and this is linear algebra. As we said in episode 2, the intersection of these planes of two planes is given by a vector. Vectors are the essence and lifeblood of linear algebra, and in fact when we get into polynomials, the idea of curves means almost nothing in linear algebra. In fact, even points on the graph will now express as vectors with coordinates. When we think of vectors, they're simply arrows that start at the origin and go to their terminal point. It can help to visualize it, but getting into fourth and higher dimensional spaces, it gets hard to do, so it's okay if you can't. Really, this video is meant to show what kinds of properties vectors have as linear analogs to variables. Well, can you add two vectors? Yes, it's actually quite easy. Given two vectors, A and B, A, B, C, and D, E, F, adding them together gives the vector A plus D, B plus E, C plus F. So you can see you just add the components together. Here's an example in 5 dimensions. 4, 9, 2, 16, 5 plus 7, 3, 12, 4, 50. You can probably just do this in less than 10 seconds in your head. It's just 11, 12, 14, 20, 55. If you were to visualize it, think of vectors both starting from the origin. Now move one so that it starts where the other ends. Now connect the origin and the end of the compound vector. That's the sum. What about subtraction? Well, it works similarly algebraically, so I'm not even going to do an example. Just subtract one from the other. The resultant is often visualized through what some call the Parallelogram Method, where you can start with both vectors, starting from the origin, then connect the second vector's end to the first one in that order. Then move the vector so that it starts at the origin. This is called the parallelogram method because if you think of the sum of the vectors like before, but both ways, that is adding v1 to v2 and v2 to v1, they end at the same point and form a rhombus-like shape called a parallelogram. This solution is the line that bisects it. Well, that's addition and subtraction, and that's pretty much all you can do. But what about multiplication and division? I'll tell you right away that there's not really any way to divide vectors, but there are 3 ways to multiply them. First, scalar multiplication simply multiplies a scalar, as in a regular vector, or a regular number, to all coordinates of the vector. This just changes the length, not the direction. As an example, we think about what 3 times 1, 2, 3 is. It isn't hard to figure out that it's 3, 6, 9. This means that 369 is a scalar multiple of 1, 2, 3. Conversely, 1, 2, 3 is also a scalar multiple of 369 because instead of dividing by 3, we think of it as multiplying by 1/3. We've already seen this when we looked at solutions of systems of equations. They're all the scalar multiples of the ones that we solved for. The other 2 methods of multiplication are between vectors. One is called the dot product, denoted u dot v. A dot product is simply a number, not a vector itself. And the sum, it is the sum of the product of each coordinate. If that sounds confusing, let's do an example. Say u is equal to 254 and v is equal to 947. Well, that just means that u dot v is equal to 2 times 9 plus 5 times 4 plus 4 times 7, which is 66. Both of these have positive dimensions, so the dot product will generally be fairly high. Well, what if you want to force 2 vectors to have another that is orthogonal, or at 90 degrees to both? This is how electromagnetism works, and if you don't know what I mean, make one hand into a finger gun, point your middle finger out to the side. Your fingers are all at 90 degrees from each other mutually. However, to do this with vectors, the original u and v don't need to be perpendicular, and it works as long as they are not scalar multiples of each other. This is what's called a cross product, written as v1 cross v2. We can write it as u cross v, but the numbers help to determine which order you put in the components. This works always in 3 dimensions, and the formula, where v is comprised of x, y, z, is y1 z2 minus y2 z1, z1 x2 minus z2 x1 x1, y2 minus x2, y1. As an example, let's find the cross product of 1, 2, 0 and 1, 1, 1. Well, putting it into the equation above, we get 2 times 1 minus 1 times 0, 0 times 1 minus 1 times 1, 1 times 1 minus 2 times 1, which is 2, negative 1, negative 1. And this will be at 90 degrees from 1, 2, 0 and 1, 1, 1. To finish, I'll tell you a little about planes. We've seen that planes can be expressed as both a sum of two vectors multiplied by parameters and as a three-variable equation. Planes can also be expressed in terms of their normal vector, which is a vector that splits off from a plane at exactly 90 degrees. Sounds like a cross product, huh? Well, funny you should think that because that's how you find it. But which vectors do you use? We're going to start by assuming that you have 3 points on the plane. In a problem, these are generally given to you, if not the vectors themselves. These each will have a three-dimensional coordinate. Next, choose one to be the origin, and make two vectors by finding the difference between the other points and the origin. These define the vectors used in the vector equation, and here we've chosen JKL to be the origin, as this is where the normal line will protrude from. Find the cross product of these vectors, and there you will have your normal vector emerging from the chosen origin. Funnily enough, the components of these are the difference. Funnily enough, the components of the normal vector to a plane will always be the same as the coefficients to its algebraic equation. Say, for example, we've defined a plane by these vectors above here, and you find the cross product from the example before. This means that the equation would be 2x minus y minus z equals d, where d is some constant, and to find it, just put in the coordinates of your origin and solve. Therefore, another word that we can give to this equation, the algebraic equation, is the normal equation.